Now next biasing technique is voltage divider bias or self bias. Now here this circuit shows the voltage divider bias. When you are designing this voltage divider bias, you have to take that R1 is must be greater than R2 to increase the stability. That means to decrease the stability factor or to increase the stability, we need to take R1 is very greater value when compared to the R2 value. If you are taking like that, then what will happen to the total resistance? That means here R1, R2 both are connected parallel. Here these two are connected parallel. Then the parallel combination of these two R1, R2 resistors. That means R1, R2 by R1 plus R2. The parallel resistance of R1 and R2 will become approximately is equal to R2 only. Approximately is equal to R2. That means very lesser value. Here I am already taking that R1 is very greater when compared to R2. Because of that, the parallel combination of R1 and R3 is approximately is equal to R2. That means very, very lesser value. Okay. Now we are going to convert this circuit into the Thevenin's equivalent circuit like this. Like this, we are going to convert the given circuit into the Thevenin's equivalent circuit. What is the Thevenin's equivalent circuit? After converting, Thevenin's voltage is connected in series with the resistor, and across the open circuit terminal, we are going to connect the remaining circuit. Now this is a remaining RC transistor and RG, and this is a converted circuit. That means here the supply voltage and remaining voltage are converted into the Thevenin's equivalent voltage, and resistors are converted to RTH. Okay, now we are going to convert this total circuit into the equivalent Thevenin circuit. That is VTH is in series with the RTH, and across these terminals we are going to connect the remaining circuit. That is this RC resistor, transistor as well as emitter resistor. Okay. Now what is this Thevenin's voltage? Thevenin's voltage is given by total voltage VCC into same resistance by the total resistance. That means this VCC into this R2 by total resistance R1 plus R2 by using voltage division rule. Okay. Total voltage into same resistance by the total resistance. And after RTH, when you are determining the RTH, here R1, R2 both are connected parallel. So that's why it is R1, R2 by R1 plus R2. Now these are your values of VTH and RTH. Okay. Now from this, if you observe the circuit, here the emitter resistor is fed back to the input. Here, this is an input now. Now this is your input. Now here this emitter resistor is given as feedback to this input. Now what type of feedback employed in this circuit? Here this feedback is negative feedback, and this is negative feedback. Why? Because if the feedback element present in the circuit is capacitor, then it is called positive feedback. And if the feedback employed in the circuit is resistor, then it is called your negative feedback. Now here the feedback element present in the circuit is resistor. If you observe here, there is emitter resistor connected in feedback to this input. That means this is a negative feedback. Okay. Now you have to keep this in your mind. Negative feedback is present in the circuit. Okay. Now I'm going to apply the KVL at this input circuit. If you apply the KVL, what will happen here? Here there is a voltage rise, and across the RTH there is a voltage drop, and across this transistor also voltage drop, across this emitter resistor also voltage drop. Now according to KVL statement, algebraic sum of the voltage rises is equal to the algebraic sum of the voltage drops. From that I am writing this equation. VTH is equal to RTH into IB. Why? Because current to this is IB. So it is RTH into IB plus VBE. Here current to this one is IE. So it is IA into RG. Now the equation is given by VTH is equal to IB into RTH plus VBE plus IA into RE. This is by using KVL statement. Okay. And already we know that emitter current is equal to the base current plus collector current. That is nothing but IE is equal to IB plus IC. Now I am substituting this IE is equal to IB plus IC in the above equation. Then what will happen here? VTH is equal to, here IE plus IB is there now. Sorry, IE is equal to IB plus IC. Substitute IE is equal to IB plus IC. Then what will happen if we take the common IB, RTH plus RE here. IB into RTH plus RE plus VB and after Here IB is completed. Next we have IC. Now that IC into RE. Is it clear to everyone? Here simply I am writing here as IB plus IC. That means IBRE plus ICRE. It will become IBRE plus ICRE. Okay, I am taking the common of IB. It will become RCH plus RE plus BBE plus IC into RE. Now here we have to determine the stability factor. Here we have to determine the stability factor. Before determining the stability factor, I am going to discuss whether the quiescent point is stable or not. Okay, whether the quiescent point is stable or not. Now here, when the circuit is connected in long duration, then the temperature is going to increase at a emitter junction as well as collector junction. Here, if the junction temperature increases, because of that, the reverse saturation current is going to increase and input voltage is going to decrease and beta factor is going to increase. Because of all these three factors, the collector current is increasing. Okay, because of the, once again I'm repeating here, because of the junction temperature increases at collector junction, the reverse saturation current is going to increase. At emitter junction, the input voltage is going to decrease and beta factor is going to increase. IC0 increases, VBE decreases, and beta is going to increase. Okay, because of these three factors, IC is increasing. That means quiescent point is unstable. Okay, now because of this voltage divider bias, how it is maintaining stable condition? Actually, it is unstable initially, but because of connection of this voltage divider bias, how it is maintaining stable? That is what we have to discuss here. Here. Now, when this IC increases, then what will happen to the emitter current and here from this circuit, from this equation? Here, if IC increases here, then IE also going to increase from this equation. If IC increases, IE increases. Now here IC is increasing, because of that IE increases. If IE increases, then what is the voltage across this resistor? That is also going to increases. Why? Because here voltage is given by IE into RE. If current through the resistor increases, then voltage also going to increases. That means IE/RE is increasing. Here, if you observe here, IE/RE is increasing. If IE/RE increases, then what will happen to the input voltage? Now for that explanation, please see here. Now here there is a source signal, input signal, feedback signal, and output signal. Now here the source signal is equal to input signal plus feedback signal. Now always the source signal is nothing but supply. The source signal is nothing but supply. Here the source signal is equal to the input signal plus feedback signal. Nothing but, if you want to determine this output, this output equation is nothing but this input plus feedback, otherwise source signal. Why? Because I want to equate the source signal is equal to the output signal. Whatever the source signal we are giving, we want same at output. How we are going to get the output as same as input? By connecting the feedback element. If you connect the feedback element, then you are going to get the source signal is equal to the output signal. That means the source signal is given by input signal plus feedback signal. Nothing but here, if this is supply voltage, this is called your input voltage. And input voltage is different, supply voltage is different. That means this is your source signal, this is your input signal. Okay, this is your feedback signal. If you observe from this circuit, this is source signal, this is input signal, this is your feedback signal. Now input signal plus feedback signal is equal to the, it must be source signal, otherwise that is equal to the output signal. You have to understand this concept here. Now here, if this input increases, then what will happen to this feedback signal? This must decrease. And why? Because source signal is constant. Source signal is constant. If we increase this input signal, VF must decrease. Similarly, if input signal decreases, VF must increase. That means the relation between input and feedback signal is inversely proportional. Input signal is inversely proportional to the feedback signal. Okay, input signal is inversely proportional to the feedback signal. If it is current signal, same concept. Here this voltage signal, here it is current signal. Same concept. Here also input signal is inversely proportional to the feedback signal. You have to remember this point. This is very, very important point. Input signal is inversely proportional to the feedback signal. Now here, by seeing this concept, I am going to explain this voltage divider bias concept. And now here, initially this output current is increasing, nothing but IC is increasing. Because of increase of IC, what will happen to the IE from this equation? IE is going to increase. If IE increases, voltage of exhaust is IE RE also going to increase. See, IE RE increases. Nothing but now this is a feedback voltage. Now this is called your feedback voltage. If feedback voltage increases, what will happen to the input voltage from this concept? If feedback voltage increases, input voltage must decrease. What is the input voltage? VBE. Now here, if this feedback signal increases, that means IE RE increases, then the input signal, nothing but VBE is going to decrease. If input voltage decreases, then what will happen to the IB, input current? Input current also going to decrease. That means IB is going to decrease. If IB decreases, then what will happen to IC? IC is going to decrease from the equation of IC is equal to beta into IB. Already you know that IC is equal to beta into IB. Nothing but gain factor is given by output current by input current. From that, output current is equal to input current into beta. Nothing but IC is equal to beta into IB. If IB decreases, IC decreases. That means, again, whatever the current increased previously, that is going to decrease because of this feedback element. Because of this feedback element, whatever the current increased, that is decreased. That means quiescent point is stable. That means quiescent point is stable. Now, because of the feedback element circuit, the quiescent point is stable in the case of voltage divider bias for long duration. Okay. Now, what will happen to this stability factor? Whether it is maintaining 1 or not. See here. Now, for that, I am taking this equation. I am differentiating with respect to IC and differentiate this above equation with respect to IC. Now here, differentiation of VTH, nothing but constant, it will become 0 is equal to dou IB by dou IC into RTH plus RE. Now here VBE is constant. When you are determining stability factor S, the input voltage and beta factors are the constants. So that's why differentiation of this constant is 0 plus dou IC by dou IC is 1 into RE. Now from this equation, I am writing the dou IB by dou IC. Now here, dou IB by dou IC is equal to minus RE by RTH plus RE. Now substitute this equation in the stability factor S. What is stability factor S? And S is given by 1 plus beta by 1 minus beta into dou IB by dou IC. Substitute here. Now S is equal to 1 plus beta by 1 minus into minus plus beta into RE by RTH plus RE. Okay. Now this is stability factor S. Now if you observe this equation, here RTH is very, very small only. Why? Because here RTH is the parallel combination of R1, R2 only. R1, R2 by R1 plus R2. Now what is this total equivalent? It is approximately is equal to R2. That means very, very small value. I already discussed this concept here. Okay. See here R1, R2 is very, very small. Sorry, a combination of R1, R2 is very, very smaller value. Okay. So that's why the RTH is very negligible value. That means you can neglect this RTH. If you neglect this RTH, then what will happen? RE is going to cancel. Here this total is equal to RE and RTH plus RE is equal to RE. Because of that, this denominator and numerator is going to cancel. And what will happen? This denominator is 1 plus beta. Now 1 plus beta is going to cancel. Now S is equal to 1 only. Now here in the case of voltage divider bias, the stability factor is 1. In the case of voltage divider bias, the stability factor is 1. So here, by using voltage divider bias, we can see the quiescent point in the stable condition.